Okay, so this is the same textbook excerpt that was uploaded to my announcement during tutorial today. I hope you already took a look at it, but this is all of the recommended questions recommended by the professor from your textbook. And right underneath, there are solutions to each of these questions. So what I really encourage you to do, now that you have the questions in one set, is to try to do some of them each day, right? Try to work on them on your own, and then look at the solutions to make sure that you're learning these actively, right? So let's try to cover some of the questions, and if among the questions that I don't cover, if you have any questions, please let me know and we can do it during tutorial. So let's just start from the beginning. Okay, for question 3, we are being told here that the company's packages have a median weight of 68 ounces and an interquartile range of 40 ounces. So before solving anything, we want to remember what this means. So the median is the middle value when all package weights are ordered from lightest to heaviest. The interquartile range measures the spread of the middle 50% of the data. Specifically, it measures IQR equals Q3 minus Q1. That's ugly. I actually don't know why I'm writing so weird. Okay. So we remember that the median is a measure of center, and the IQR is a measure about spread or variability, right? So now part A, what the company is gonna do is they're gonna add a flyer that weighs 4 ounces to every package. And the key idea here is that adding the same constant, which is 4 ounces, to every observation, right? Because that's what it's doing. This shifts the entire distribution, but it does not impact spread, because just think of it as maybe you have a normal distribution here and then you add 4 to each observation and now you have a normal distribution here. It's meant to be exactly the same, but okay. So based on this, it seems like you just have to add 4 to the median, and the IQR would not change because whatever this Q3 and Q1 values were, they had 4 added to them. So when you subtract them, it cancels out. So the median, the new median will be 72 ounces. The new IQR will still be 40 ounces. For part B, the company now records weights in pounds instead of ounces. So now they're going to try to use a different measure, and this is different from part A because we are not adding anymore. We are now scaling it, or scaling means dividing or multiplying, right, by a certain constant. So what you need to keep in mind here is that multiplying or dividing, okay, I need to write write somewhere different. So, multiplying or dividing by a constant, and here you're assuming multiplying or dividing every observation by a constant, changes both the spread and the mean or center, median. Yeah, so it seems like 1 pound is equal to 16 ounces. So that means if we had maybe median was 672 from our part A, because we added 4. Now this was in ounces. Now our new median will be in terms of pounds, so 72 divided by 16, right? So here you have the complete answers. So in short, whenever a problem is modifying every observation in the data set, you can ask yourself, or am I shifting the data or am I scaling the data? And you know, it's different depending on if you're adding and subtracting or multiplying and dividing when it comes to how the center and the spread are impacted, okay? So let's try to do question 5. The EPA fuel economy estimates for automobile models tested recently predicted a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon for highway driving. Assume that a normal model can be applied. See how it's saying that assume that a normal model can be applied? You can't like go around applying the normal model to everything unless it tells you to, or unless you want to assume that, right? So just remember that. So let's now do it more properly. So now the mean, which we denote by mu, is equals 24.8 mpg. And the standard deviation is denoted by, no, not denoted by, sigma equals 6.2 mpg, right? So let's say our random variable x is x, and then we have to specify what x is, remember? So it is fuel economy estimates, right? I don't actually, okay, yeah. So whatever x is normally distributed with 24.8, 6.2, this normal distribution. Now we want to draw the standard normal. No, not the standard normal. Or now we want to sort of sketch this normal distribution, okay? And I would, rather than doing that, I'll show you how they sketched it. So here they sketched it. 24.8 is the mean, as you can see. And each part here, right? This is one standard deviation. So each part here is 6.2. Yeah? And part A is asking us to draw the model, clearly label it, and show the what 68, 95, 99.7 rule predicts. So what is that rule? If we go back to our material, we see this rule here. it tells us that in a normal model, approximately 68% of values fall within one standard deviation of the mean. Approximately 95% fall within two standard deviations of the mean, and approximately 99.7% fall within three standard deviations of the mean. So now they're trying to get you to use this fact to solve this problem, okay? So here they labeled the two standard deviation with 95%, one standard deviation with 68%, okay? And they labeled the 99.7% here. So you have now clearly labeled it, showing what the rule predicts. Part B tells us that, and you understand how you're going to find these values, right? So you just start from the mean, 24.8, right? That's your mean. You minus 6.2, right? And that's how you get 18.6. That this is the value that is one standard deviation below the mean. And then you can find the one standard deviation above the mean, which will be 31.0. And then you can find two standard deviations below the mean. So that is two standard deviations below the mean, 12.4, and then two standard deviations above the mean, 37.2, etc. Okay? That's how we're coming up with the values. Part B is saying, in what interval would you expect the central 68% of auras to be found? So now it's easy, right? Because you already know what interval. So this is the interval where you would find 68%. So it's from 18.6 to 31.0. How did they say it? Oh, they just said it in words. Yeah? Because maybe you want to write it as interval, right? Because they asked for an interval, you can say 18.6 to 31, right? Or 18.6 to 31. Because inclusive or not inclusive doesn't really matter too much here, because this is a continuous distribution and the probability that it equals any given value exactly is 0, so it doesn't matter in that way, okay? Part C asks us about what % of auras should get more than 31 mpg. So we know that 31 mpg is here, so more than this is what %? Because until now, so what we have here, right? The way to get this is we know that this is 50%, right? If we cut it entirely if we cut it entire, this is actually so annoying, right? If we cut it entirely in half, then this is 0.5, 50%. But what about this value here? This value is half of 68%, so 34. You add to 50 your 34, that is 84, and then you subtract from 1, to get this one, because the whole area under the curve must be 1. That means 16, right? 16% of cars are expected to have highway fuel economy above that amount, okay? Now for part D, about what percent of cars should get between 31 and 37.2 mpg. So now we want between 31 and 37.2. Okay, so can I write on this? Oh, okay, now when I write on it, it's okay. That's so strange. Okay. So we're asked 31. So we know that 31 is what? Is 1 standard deviation above the mean, right? And we know that 37.2 is 2 standard deviation above the mean. Now we're wondering what lies between these values. So if 95% is within 2 standard deviation above the mean, then there's just 5% that is outside. So each of the tails is worth 2.5. So if 95% is if 95% is above the is within 2 standard deviation, then each tail to the right of 2 standard deviation, these areas, each of these are 2.5%. So the area to the right of plus 2 standard deviation, or 37.2, is 2.5%. And we already know that the area to the right of this one here is 16%. So the area between these values is 16% minus 2.5%. And that is 13.5%. So the key here is to just find these values correctly, and then using these 68, 95, 99.7 percentages, try to find all of these. I don't know what's happening with this. Okay. How would you do part E? The part E asks us the worst 2.5%. So the worst 2.5% means the lowest of the mileages, which is the left tail. And again, using the 95% rule again, if this 95% is in the middle within 2 standard deviation, that leaves 5% in the tails, so each tail is worth 2.5%. So the cutoff for the bottom 2.5% is at -2 standard deviation. That is 24.8 minus 2 times the standard deviation, that is 12.4. So the worst 2.5% of cars are expected to get below 12.4, mpg. Okay, so just the strategy here is just to convert each of these values to how many standard deviations it is from the mean, or you can do it using the graph of that you sketch, and then use the 68, 95, 99.7 rule. Okay, if you attempt it on your own, I think you can all do it. Okay. Let's do part 7. Oh, there was one about payroll. Okay, let's do this one. Okay, let's read the problem carefully. So we're given summary statistics for weekly salaries at a company. We have the low salary as 300, mean 700, median, range, IQR, first quartile, standard deviation. So we want to answer 4 questions using just only these numbers, okay? So for the shape, part A. Do we think the salary distribution is symmetric, left skewed, or right skewed? So a fast way to compare is to compare the mean and the median, because typically in a right skewed distribution, we have because there might be a few very large values here, they will pull the mean above the median. If there is a left skewed distribution, because there might be a lot of small values here, they will pull the mean below the median. Because the median is the middle number, it tends to stay more near the center when we have skewed values, right? So here we have mean 700 and median 500. So the mean is bigger, so maybe there are some people who are earning very high amounts that is pulling the average up, and we might assume or hypothesize that the distribution is skewed to the right. Part B asks us, between what 2 values are the middle 50% of the salaries found? So the middle 50% means it goes from Q1 to Q3, right? So the interquartile range. So they gave us Q1 and Q3 already, first quartile. They gave us only Q1. So we know that for part B, Q1 is equal to 350. So that means our IQR, which is Q3 minus Q1, should equal 600, right? Because we're given that it's 600. So now we can solve for Q3. So the middle 50% of salaries are between 350 to 950. Okay, so for part C, it says company gives every employee $50. So when this is the same question as we had before, when you add a constant, all of the center measures shift by the constant. But the spread measures stay the same. Because it's like the whole distribution is just sliding to the right, right? So you can write down that the minimum will become, for example, 300 plus 50. Mean will be 700 plus 50. Median will be 500 plus 50. Q1 will be 350 plus 50. And meanwhile, range, IQR don't shift. Now for part D, instead of giving a fixed raise, now there's 10% raise, right? So that means new salary is going to be equal to, here you have a new salary, which is going to be equal to 1.10 times old salary. And this, as we can see, is we're multiplying, so we're shifting, and when we're shifting, the measures of center are multiplied by C, and the measures of spread also are multiplied by C. So C, I mean as in the as the constant C, right? So you would basically just multiply everything that's here, that's given here, by 1.1. Let's see if that's correct. Okay, seems to be correct. Yeah? Okay, now let's do 50. So a town's January high temperatures average 2 degrees Celsius, with a standard deviation of 6 degrees Celsius, while in July the mean high temperature is 24 degrees, standard deviation is 5 degrees. Which month is it more unusual to have a day with a high temperature of 13 Celsius? So when we say unusual, we mean unusual in terms of relative to typical, right? Not just raw unit far from the mean, right? So we essentially we want to be comparing z-scores, and as we know, z-scores are essentially sum x minus the mean over the standard deviation. So we want to compute how many standard deviations these 13 degrees is from the mean in January and July. So let's do for January, and our January z-score is going to be equal to, we're given that our mean is 13. No, the value we're interested in is 13, and we're given that our mean is 2, and we're given that our standard deviation is 6. So this means 11 over 6, whatever this is. And in July, we're given that the mean is 24, standard deviation is 5, so that leaves us with negative 2.2. Okay, so is it 2.2? Yeah. So now we can try to, this one is 1.8. Okay, let's say this is 1.8, this is 2.2. So which one's farther from the mean? Because we can just compare the sort of absolute values, right, in our head. We know that this one is farther from 0 than this one is, right? So this one is negative 2.2 is farther from 0. So the takeaway is that from just reading the problem, right, it seems like 13 here is 11 degrees far from 2, but also 11 degrees far from 24. But relatively speaking, it's rarer in July because July has a smaller standard deviation, so the same difference is more extreme because of it, even though it's not considerably higher, lower standard deviation, right? So that's very interesting. Okay. And I think 17 goes over the same thing. I really encourage you to do it on your own. 19, the same thing. So many problems about cattle. Okay, I think these were the main ideas that you needed to understand to be able to approach the problem that we've covered already. So now I would really encourage you to try to do it on your own. The only thing maybe that might be unusual is this problem 9 here, because here you're given a distribution of song lengths and you want to know if it's normal using what they call the normal probability plot, but it's also known as many different names, right? Like QQ plot. So this is basically you're doing all this to be able to tell if a distribution might plausibly be normally distributed. So if the distribution is normal, okay, the thing you have to remember is if the distribution is approximately normal, the points on a normal probability plot should roughly fall on the blue straight line. This is the straight line, okay? So if the points here that are your actual observations, if they fall along the straight line without being upward sloping or downward sloping or having shapes of different types, if you don't see curvature, then it's a sign that normal distribution is reasonable. But if it does have curvature, then that's a sort of a bad sign. So if we look at this here, if we look at this plot, we see that the red is not forming a straight line. So we see the upward sloping curvature, which maybe tell us that the observed songs here and maybe here are sort of deviating from what we would expect from the normal distribution, okay? So we conclude that it might probably not be normal. How does it differ from the normal? So it's if we see the right tail of the plot, there are many points above the line, and this means that the longest songs, so these are the longest actual observed songs, right? These are much longer than what the normal distribution would expect. So this line is what the normal distribution would expect because it's drawn right along the normal quantile here. So for extremely small values, we expect it to be less common, right? In terms of normal quantiles. For middle values, we expect it to be slightly more common. For very high values, we expect it to be less common, right? So this one, you would just, I think, you would just conclude that it seems right skewed. I think that's what the question's asking for. Let's check. The normal probability plot is not straight, so there is evidence that the distribution is not normal. Distribution of lengths of songs appears to be skewed to the right. Shows that longer songs in the library are much longer than those predicted by the normal. Song lengths are much longer than their quantile score would predict. So, these are song lengths. These are the long songs, and this is what's predicted by the normal. So the long songs are much more longer than what's predicted, right? Okay, so this was maybe the only foundational piece that we didn't cover yet, because every other problem here now, you can derive the solution based on the principles that we worked with in the first few, okay? So do try that, and please let me know if you have any questions, okay? Bye.